Hello and welcome back to Calculus 2, section 6.7, physical applications, or just physics. So we're going to discuss some of the physical applications that we can do with these integrals. And for the purposes of exam, if any of these advanced physical formulas pop up on the test, I'm inclined to give those to you, but no formula sheets of any kind. Again, no calculators and stuff is to be observed for exams. I might provide the formula for, a physical concept because we are here to calculate integrals and stuff, unfortunately. So we start this discussion by talking about density and mass. Then we shift into the forces and we shift into work. And then we'll see what else we can do. So first of all, talking about the mass and talking about the weight, those are not same concepts. To understand mass is a little bit trickier because your mass is the same on the moon and the Mars and the surface of the sun, where you get scorched, and the Earth. Mass is always the same. It's a constant. Where the weight is actually the force, which is mass times acceleration of gravity. So if for whatever reason, being skinny and looking like those freaks from magazines is appealing, all you need to do is to jump to the moon and measure yourself there, and you will be instantaneously, half of your weight. Looking at the mass, I like to describe mass as a quantification of physical existence. If something exists and you can touch it, well, even if it's, atoms and stuff, it possesses mass. So I like to call it quantification of physical existence because you can measure the mass, and in some sense it's how heavy you are, right, or how heavy something is. We measure it in grams as a unit, but then you have milligrams for pills, and you have kilograms to measure humans and other livestock. So the story of density now is that mass is equal to density times volume. And many of these formulas in physics, especially before you venture into university physics or what we call here engineering physics, many of these formulas are done on uniform motion or uniform density or so on. So you just plug numbers in, you're done. But what happens when the objects are not of uniform density? Right? We should be able to compute things even if they don't have uniform density. So, for instance, you take a look at the basketball, and basketball would have a uniform density because it is symmetric from all sides, filled with air, right? So, uniform density. Anything that has the same material and built from the same material throughout is going to be uniform density. Soup is not, right? Human body is not uniform density. There are certain parts of the body that are denser than others. So density can be variable, and then you have alloys and all other things. So density can be a variable, and we will institute a density function, right, that shows how the density changes within an object and then we will use that to compute the mass. So let's see. So for the mass of the one-dimensional object, now this is the integral that you should know, because this is not per se physics, it's common sense. Mass should be the integral of density function. So this rho of x is density function.
What is that?
Rho.
Rho?
Rho, Greek letter. Instead of r. Well, actually r is instead of rho. So rho of x is the density function, and when you integrate, now this is a one-dimensional object. What would that be? Like a long rod, something that, you know, other three dimensions would not contribute too much. You see, take that big white, whatever the hell that is on the wall, but the longest one, right? Its length is far longer than width or a height. So technically that can be regarded as the one-dimensional object, even though we know it's a 3D object, right? You can see the height and the width. But the length is so dominant over there that you will have issues balancing that thing lengthwise, not the widthwise, right? So if you can imagine objects like that, or take, let's say, you take train tracks apart, you take one of those long rails, right? That will have a lot of length to it and not so much width or height. So those other two dimensions are technically negligible. So, you know, calculating this kind of stuff for 1D does make sense in some cases. But, you know, this formula is for 1D, and you are going to see 2D and 3D formulas when you take Calc 3 next semester. Or summer. Whatever. So, if the object is of uniform density, then the formula on top, one in black, is the formula to compute. But if you compute with the red one, it will still work out and be the same number. However, the black formula up there is completely useless if you have variable density, because it doesn't allow you to plug in any kind of functions, where the one on the bottom uses the density function integral. So now, they say a mass from a variable density, a thin 2-meter bar represented by the interval, right, 0 to 2, because 2 meters, is made on an alloy whose density of units, or kilogram per meter, is given by, so they give you the, density rho function as 1 plus x squared. So this is what we have. We have rho is equal to 1 plus x squared. We're working on an example. And that's happening on the interval 0 to 2. Now that means over there 2 meters long. And we would like to see what is the mass of it, right? So the mass is going to be the integral from 0 to 2, 1 plus x squared dx. You integrate everything, it's x plus x cubed over 3 from 0 to 2, which is clearly 14/3 in kilograms. So 14/3 in kilograms is what we have for this particular rod. Now, I want to see how this actually not looks like, but how is this density distributed, right? Because density, right, is given as kilograms divided by units of volume, whatever units you use, meters cubed or liters, depending on which units you have as input. So I just want to draw this rod that starts at 0, ends at 2, has 1 somewhere along the line. And as I'm looking at the function, the distribution of this density, at 0 meters, at the beginning of the rod, like the first few parts, the density is rho equals, so rho of 0 is equal to what? 1. What's rho at 1? And what's rho at 2? 5. So you see that the density grows. The object is denser as you move from 0 to 2, because that's how the density function looks like, 1 plus x squared. Now obviously you can compute for 1/2 and 3/2, right, get more numbers in, but the density grows. And we know that the mass of the object is 14 divided by 3 is almost 5 kilograms. 5 kilograms is nothing. I'm over 100. So 5 kilograms is like, I don't know, 12 pounds. So not a big deal. Even though it's wrong, we still say a kilogram is about 2.2 pounds. Which makes no sense because they're not even the same. They're not the same concept, right? But we still do it, unfortunately. You can convert between the, one is mass, kilograms is mass, and pounds is the force. When you buy kilogram of bananas, you paid for bananas. When you buy a pound of bananas, you paid for the force that pushed the scale, because pounds is the force. All right, so now that we know how to compute the mass, we're going to talk about work. Big topic, work. And we again start with a basic notion from basic physics course, where we say that the work is the force times the distance. And again, that's just the perfect world, which is not there. If you are pushing something heavy, you are going to go at it, and then you're going to get tired and tired and tired, right? This is how force actually looks when you push something. It is not possible, humanly possible, to push with a constant force, which is actually this equation here. You are going to have some variable force that depends either on time of pushing, or we'll say f of x, which is how far did you actually go. The further you push, the more tired you get, and eventually you stop pushing or you got to your destination. So this would be the constant force. So this is just F. It's not a function. It's just a number, right, that you're pushing. You can make machines push with a constant form. So for machines, the black equation from basic physics is okay. But in our case, or if you look at the horse or something, right, you are going to have that the work, and this is the red equation now, is equal to the integral, the force function, dx from A to B. So F is the force function. So now what's happening here? Say you have a crate. Gotta look at the artist over there. Get the. I know that arm is too long, but such is life. Hard hat. The motion captured with the little lines. Scarf, maybe. I don't know. Happy. Nose. All right. So this poor fellow. A little bit fatter. So this poor fellow is doing the work, right? So when you're doing the work, what do we have? You have the force, and the force in this case can be decomposed over here, right? Because the force will be exerted down the arm that it's pushing onto the crate, which will have two vector components and so on. But it's only the vector component that is horizontal, that is parallel to the floor, that actually does the work in this case. So we can get that with trig. The crate, you know, depending on how picky the problems are, does it have, that would take consideration friction and all the other stuff. What's most important part here is to understand the connection between the integral that you see and what's happening on the picture. You see, the portion of the, let's say, well, actually, wait, hold on. A to B, actually, A to B. So this part over here is how far the crate goes. And that part there is your famous delta x, which was b minus a over n, which leads into dx part. So how far the object goes is captured with the limits a and b, and then you have the force F, which is the function. So as I said, as you're getting more and more tired, right, the force is weakening, and we can capture that with a function, right? I can draw some kind of function that is decreasing. Usually it's not linear. Usually you start getting, I don't know, slowly tired, and then you really get tired. So maybe some kind of negative x squared could play a role in something like that. So that's the idea of the entire, right? So I'll just say getting tired. Less force applied. So that's force in time. So let's take a look at all of the different examples, flavors. There's a lot of cool stuff that we can do. So the first one is with springs. You're familiar with the concept of a spring, I hope. It's the same crate, just a lower resolution. So this crate, which is when you leave the spring alone, it goes into that equilibrium, right? And it's just going to stay there. But we can actually stretch it to some position, to some new position x0, in which case dx happened, which means some work had to be put in. This crate is not going to move on its own. It was happy, it's equilibrium, right? The preferred state of technically everything and anything. So what we have here is, first we have the Hooke's law, which states that the force function is equal to kx. Now you will find a lot of places where they put negative kx because the springs will always like to do opposite of what you want, right? If you compress the spring, spring is pushing out. If you stretch the spring, spring is pulling in, just like rubber bands, right? So in many cases and applications, you're going to see a minus sign there. In some, you will not. So this textbook doesn't have it. So now you see that you have all of the ingredients to actually calculate the integral, because now you know what the function is that you have to plug in inside that integral of f of x. So you will replace f of x with kx, but hold on. Can we find the k? K we can find if we have enough information given. So technically, K measures the stiffness of the spring, right? So if you take, I don't know, a spring out of the shock of the car, and you take a spring out of your pen, yeah, one of those will be easy to squish and the other one not so much, all right? So the difference between the two, sure, you see the materials and the strength and the size, but the difference between those two in the simplest terms is K. That's all it is, right? So you look at K and say, oh yeah, that's the car spring, oh yeah, that's the train spring, oh yeah, that's the spring that we put in a pen. So, so now, this thing is called the spring constant. And what it does is it describes, it quantifies in some sense the spring. So you can always compute that because you know either how much force was used to move the object for a little bit, or it's already given in a chart or a table that you refer to, that's when you're an engineer. So it says, compressing a spring. This is the example now. Suppose that the force of 10 newtons is required to stretch a spring 0.1 meters. So it's going to take 10 newtons to move the object 0.1. Well, by Hooke's law, immediately, you have that 10 newtons was used to move the object 0.1 meters. So from here you can clearly see that K is 100. What? Newton per meter. So we can find this K if we are given this type of information. How much force it takes to move it, how far. So it took 10 newtons to move it 10 centimeters, right? And then plug that in the formula, we get that the spring constant is K equals 100 Newton over meter. Cool. So now we have that, and the questions are, Well, that was part A. What's the spring constant? Part B says us how much work is needed to compress the spring 0.5 from the equilibrium position. So how much work is needed to compress spring 0.5 meters from equilibrium point? Well, I know that the integral from 0.5 meters, right? So I have to go, so it's a point of reference now. I'm going to draw this. And I'm going to say that this over here is the equilibrium. So that's the equilibrium point. So if that's the equilibrium point, that's where the big fat zero goes. They say they want to stretch this. No, yeah. Compress, sorry. They want to compress 0.5 meters. So which way do I go? Left or right? Left. So this thing has to go to the left. All right, cool. So those are your limits of integration from 0 to negative 0.5. The hell negative? Why? Because left of 0, right? Equilibrium is 0. That's the center of the universe at that point. And there is positive numbers to the right and negative numbers to the left. If you're compressing it, you're going to go from 0 to negative 5. If you are stretching it, you're going to go from 0 to whatever you stretch. We know that the function is given as kx, so k is 100. So that's 50x squared, 0 to negative 0.5. And the work is clearly 12.5 Newton meters. So I'm meditating from. So how much work is needed to stretch? The spring quarter of a meter. Again, from equilibrium position. It's the same spring, so you're using a still same 100 spring constant. Try this one on your own. This O is terrible. That's O. So now we go the other way, right? Just the integral from 0 to 0.25 from 100x dx, which is still 50x squared from 0 to 0.25. And what do we get? 3.125. Newton meters, not potatoes. No, just newtons times meter. Newton. Oh, that was for the spring constant is Newton divided by meters. D. Stretch from 0.1 to 0.25 meters. What's the work? It's a little bit of Yoda for you. $3.115. Got a different number? Or one.
I think I did it. I just subtracted from the previous one.
Why?
You just change the lower, the a from 0 to 1.0.1. So that case, it will just be 0.01. So you just subtract it from 3.125.
Nice.
You can use the function difference for each.
You can do the integral. But if you have already two results and you know the theorem from Calc 1, oh wait, but this doesn't go to 0.1.
Pick up 0.1 subtracted from the one you did.
Yeah.
2.6.
2.655. Okay. But what I'm going to do is I'm going to say 0.1 to 0.25, like this. You can do it with subtraction as well if you want to. 100x dx, which is 50x squared, 0.1 to 0.25. And what did you say was the answer? Like this?
Yeah.
Newton meters. So what else you can do, since you have this result, you can calculate 0 to 0.1 and subtract it from here, which would drop this to that number. So you can do it by subtraction as well.
How else would you do it? Subtract it?
No, yeah. In this case, you compute at 0.1 and 0.25. The other case, you just compute at 0.1, but they still have the subtraction. So I don't think you computationally save any time, but it's a good exercise of the mind. Lifting problems. Is it going to be the same if you lift a 10-pound rock and a 10-pound chain. It's going to be the same.
Depends on the length. What's the gravity on each?
Well, the stone is round and the chain is long, so yes.
With like you're picking up one end of the chain and the other end is just dangling?
Yeah.
You're picking up.
So you will take maybe the first two links. So one hand you pick up the 10-pound rock, the other one you pick up the chain and you lift at the same time. No, why not? The rock is going to be heavier.
Less volume.
Well, rock is heavier. Why? Because you're picking up the entire 10 pounds. What's happening with the chain? Yeah, it's becoming heavier as you lift higher, right? Because more and more links are what you have to hold now. When the chain is entirely on the ground and you're just holding two links, well, you don't even feel it. But then as soon as you start lifting, the more weight is added as you go up. Work, potential energy, right? It's mass of the thing you're lifting times the height to which you're lifting, and then times the gravity, which is down, mgh. So that's the lifting problem. The work is obviously force times the gravity, and force times the distance. And what you have is mg, and then call it y or h. So the y is how high up you lift the object, and then obviously you have mass times gravity there. That's the actual force, which is the weight due to gravity. Weight is force. All right, cool. So now, how do we do these problems? How would you do a problem that has a chain in it? Let's say you want to lift the chain. It's a stand you take to lift the chain. The chain right there. Now I'll give you a hard hat again because working hard, right? So now, what's happening here? This link is dying. There we go. So you're lifting this chain. There is the height. There's the mass of the chain. Well, height, which is y actually. Yeah, I'm just going to put y so we're not confusing too many letters. And you have the gravity that's pulling down. So if you want to pick up the entire chain, say the chain is 1 meter long or 2 meters long, because my height is about 192 or so. So 2 meters is, a little bit above my head is where the 2 meters is. So the chain is as long as I am tall. So say you want to pick up 2 meters of chain. How much work is done in picking up the chain? Now I will see what else we need once I will add whatever we need. So we know that the work, as the integral is from a to b, now we're lifting straight up, so this integral is going to be in terms of y. Maybe I should put C and D. Yeah, whatever. And the question is mass of the chain, right? N times G. And then what goes in parentheses? It's going to be 2 minus Y. Why?
2 meters minus y. So y is the distance from your hand to the chain, and 2 is what you're gonna. It's 2 is the 2 meters I. So minus, well, like you already have, times that you need.
Why 2 minus Y? Yes.
Because each point of the chain is a different distance from the ground, so you need to calculate the ones that are on every point.
Yeah, but why 2 minus Y? Why 2 minus Y? Everything you both said is correct. But it's not answering my question. Why 2 minus Y?
Nothing on the y-axis.
Why is it not Y plus 2? Why is it not 2 times Y? Why it's not Y squared? Why is it 2 minus Y? Let me put it that way.
Because we have already defined that amount of chain that the y, I mean, the total length of the chain is 2 meters. We've already picked up the y amount, the y length, so it's that subtracted from the total length. But you don't know what it is, that's why it's a variable.
So we have to pick up everything, right?
I see. When you pick up the whole chain, you can't lift it any higher, so that's sort of zero.
Yes. There's no more work to be done. The work has to go down to 0 as soon as you lift, because the work is happening while you're lifting, right? And as soon as I get here, the work has to go to 0 because work has been done. You lifted the chain, right? So when the chain is on the ground, then the height you lifted is 0 because you haven't done anything yet. So 2 minus 2 will give you, sorry, 2 minus 0 because you didn't lift anything. So this is the floor, and I'm lifting this chain. I haven't lifted anything yet. So there is still 2 meters to go. So 2 minus 2 is 0. Sorry. My height, the hand is at 0. So 2 minus 0, right? And now, as I'm lifting, right, it's becoming heavier and heavier and heavier. And then when I lift everything, right, 2 minus 2 gives me 0 because the work is done. The whole chain was lifted. So, and the beautiful thing about the limits is going to be that you don't actually have to lift the whole thing. You can lift a half, you can lift whatever. That's going to give you 0 to 2 over here. Whatever the mass times G times 2 minus Y dy, and you just compute for the lifting the entire chain. Yes?
Aren't you technically continuing to do work to keep the chain in that position? Or are you going to, I mean, sometimes...
Yeah, this is just the lifting part. At the point when you lifted the entire chain, it's going. This is efficiency, one and done. When you lift the entire chain is lifted, and the force becomes constant. In which case, this formula takes over. There is no more change in. So we don't require calculus any further. Calculus is required for the portion only as you're lifting things, right? Where there is a change in mass, where there is a change in height, where there is these things are happening. And obviously the very negligible change in gravity, right? Constant, because the closer you are to the center of the Earth, the lower gravitational pull, the further away you are high. Oh, sorry, the other way around. Yes?
We can just take natural gravity right out of the already.
Yes. So all I need to do is mg integral 0 to 2 of 2 minus y dy, which is mg integral, so that's 2y minus y squared over 2 from 0 to 2. We only plug in 2, so it's mg 4 minus 2, which is 2 mg in this case. Now you know how heavy the chain is and how much the gravity is, 9.81. Well, depending on which. What?
Would it be negative gravity?
No, it's just positive. Because you're lifting it up. The motion is up. Now you can actually compute also if you want to lift it halfway, so 0 to 1. Maybe you just want to compute how much work was done from, I don't know, this is 0 to 2, so maybe 1.3 to 2, because someone else was lifting up to 1.3, they got tired, and that's what you picked up. Right, so you just want to see how much work you did to get paid for that portion. Yes?
What if you're lifting it up to like,
You can with these limits, you can lift anywhere you want. The length of the chain is encoded here. If you want to keep lifting it forever, right, you can use, as I said, this equation here, because the entire thing now becomes, there's no more change in it, because once you lift the entire object off of the ground, you might as well take that 2-meter long or 2-mile long chain and compress it into a point that is, I don't know, 10 kilograms. So can you do it with calculus? Sure, just put the limit up to 5, how far you want to go, right? Because the length of the chain is 2 minus y, and I just say I just want to lift the chain, so 0 to 2, because that's enough for me to lift the chain. But if you want to lift it one, and next problems are coming, so that's exactly going to address that. You did the class prep, right? Yeah. So the lifting requires calculus because part of the chain or part of the rope is on the ground. Where, right? Good, that's it. All right. And now we can use these lifting problems in a more advanced setting to figure out how much work we're going to require to pump the water out of the flooded basement, to pump the water out of the pool, to pump the gasoline from the underground tanks into the cars on gas stations, right? So all of these things can be computed. It's going to depend on the geometry of the tank. And the reason why you want to compute this work is it's closely related to the horsepower of the pump. So when you have a basement and when you have a properly engineered drain system, right, you will have a sub pump, and you will have the hole for it, and all of that will be the right and appropriate size for the basement. And then you will have a 1/4 horsepower motor, right? Because 1/3 or half, right? Depending on how much water needs to push out, how quickly, and all of that stuff. Now, all of that depends on the geometry of the shape that you are trying, that's stored, whatever it is. It could be water, it could be gasoline, it could be whatever else that you're trying to pump out. So the first example might be survival technique, right? You have a can, and you have a straw, and you just want to get the liquid out and then into your system and survive, right? We all are familiar with those survival techniques. So I would like to, let me first write the formula so that we understand the formula, and then I will go on and do those more advanced problems that you might be responsible for. So the work in this case would be the integral a to b of rho g a of x, or actually y, because again it's height, d of y and dy. And to explain this formula, let me put this formula first in the red box as very important. And then to talk about this, let's just take a look at the basic thing. You have the can and you have the straw, and then you're going to drink. Right? So this is a can, and there is a straw in the can, and there is the liquid inside. So there is a liquid in there, and you're familiar with the concept of what's going to happen. It goes up. So how much work are you doing to pump this up? So how tall is a can? We do not have a can. No one has a can. It's all. Does anyone ever drink? It's like, what's this water? Guys, that's for cleaning. You have anything serious? Who drinks water? I go in a coffee cup. Alright, fine. Okay. Can. Now it's a can, all right? So looking at the can, when you put the straw in, it goes all the way to the bottom. So all of the Sprite, all right, that you're getting out, it's going to start from the bottom and it's going to go up the tube out. So clearly there is the area, right, cross-section area, and that's this puppy here. And then there is how high it has to go, which is this puppy here. And then there's the gravity that is pushing down and to some extent helping. And then there is also rho, which is the type of the fluid that is coming out, because it's not the same water, Coke, gasoline, blood. Like, very hard to use the straw because blood is, yes.
Can you just go over the difference between A to B and dy, or d of y?
Yes. So we also have how much stuff do you have. You're going to drink the whole can. It's the height of the can. So say, I don't know, how tall is the can? 6 inches? Right, 6 inches, let's say. So 0 to 6. Can was full, and I'm drinking everything in one sip. Right? That's how I do it. I don't know you, amateurs. So A to B would be 0 to 6, but then the straw is going to be maybe 8 inches. So there's going to be 8 minus y. The same thing like earlier we had 2 minus y. So those are the ones that that we have. And I'll talk about these concepts more. So to solve this particular, yeah.
P looking thing at the beginning?
Rho?
Yeah, that's the type of liquid.
Yeah. So it's a density. So you are talking about, right, the blood is much denser than water. So it's much easier. That's why we all drink water, because it's easier to drink than straw. Blood is not easy to drink, but it's heavier. The tar would be even worse. Get the tar to straw, forget it. Create singularity, the problem is closed. All right, so looking at this, I will say that this can is 6 inches tall, that the straw is going to end up at 8 inches. What's the radius of the can?
Like an inch, 2 inches.
2 inches. Sold. 2 inches. So how much work do I go? How much work do I have to do to empty this can? Well, for me, zero. It's just like that. So what do we do? Well, the work is going to be drinking the whole can. So 0 to 6, right? This is the ground, right? Where y is equal to 0. Well, I have it on the other side. So the can was full. Now, can could be half, right? Which means 0 to 3 or 0 to 4 or something. But I'm drinking the whole thing. So 0 to 6, rho, it's a mysterious liquid inside. Gravity is there still. Now area. Well, area,
Just one slice of that.
slice of this, yes. So this is the area. In this case, very easy. 4 pi, exactly. 2 squared pi, r squared pi, or pi r squared. You are used to pi r squared, right? Pi r squared. And 8 minus y, dy.
Will this only work when it's a cylinder? Or
No. Works with anything.
any kind of liquid?
Yeah. It's going to be epic by the time we do these other shapes. And you just integrate. So this is equal to 4 pi rho g, though that's all constants. And you are only integrating 8 minus y dy, which is 4 pi rho g, 8y minus y squared over 2, computed from 0 to 6, and all of that is equal to some number, Newton meters, and we're done. Or feet, right? Foot pound. Now, much more interesting is,
Could you say joule instead of unit?
yeah, all calories. Yep. Go ahead, convert the units. Impress me. Yes?
You know what this is? Is it the size of the can or the liquid?
Liquid.
Alright, so the picture is wrong.
Why?
You didn't know.
Oh, yeah, I didn't fill it all the way up. Yeah. Sure. Yep. I'll just say whole can, and as you said, picture is wrong. Happy? I wrote it in blood right there. All right. Now, let's do something else. Here, a conical tank. Why would you have a conical tank like this in the ground? What do you mean?
You can like kind of drive it in easier.
Yeah, hammer it in.
You might damage the tank, but it's in there.
Yeah, it's in there. It's good. Just cover it with dirt and it's going to be good. Here's the nozzle. Yeah. It's good, all right? Whatever. I'll color it. Whatever. So we have a tank, conical tank, let's say 10 meters tall. Let's say that the nozzle is at 2 meters above the ground. So that's going to be at the level of 12 meters. And say that the liquid is at 7-meter mark. So you have liquid underneath. That's all liquid. You want to empty all. You want to empty all. And yeah, what's the work involved? Make sure the stream is still live. Yep, still live. Good. So what do we do? So we first have to figure out, right, all of the pieces that go in the equation. And the craziest one to figure out now is the area over here. Because what's happening with the area? It changes as the water level goes down. This circle that is on top, which is the area, is becoming smaller. That was not a case here. It was always the same cross-sectional area, which is why we had the constant over here, 4 pi, right? But now that's not the case, which is the reason that you see that area is going to be a function of the height in some way. So for these problems, that's always the scariest piece. Everything else is standard. You're always going to have the same setup in terms of the work is equal to A to B, rho, G, and then the scary piece goes here, and then the height minus Y, dy. You already know that this over here is 12. You already know that this is 0. You already know that this is 7 because liquid is up to 7. Rho G are constants. So the only missing piece is the area. So now we have to figure out how to express this area in terms of the height y. In terms of the height y. So how do we do that? Do what?
Area of cone is 1 by 3 pi r square x. So you just take x and put the value according to,
But it's changing. You gave me the stationary formula. And the area is the area of the circle, right? So we actually have to figure out the relationship between the lowercase r and this y here. Nah. We have similar triangles.
Oh, this is where we're doing the related weights again?
Nope. You're welcome. You see, guys, this is the major radius, and that major radius is always... Oh, I didn't give you that information. Damn. What is it? What is this radius here? 4 meters? Whatever. 4 meters, all right? So that's always 4. We have the height, capital H, which is always 10. We have the low, and now we have a variable height y, because yeah, it's going to start at 7, but it's going to change. It's going to drop down. And we have the small radius r, which is the one that goes in the formula. So we know that the area of the circle is pi r squared. But I need to make it as area of y. So if I write the proportion from this one, which is capital H is to big R, what small h is to small r, and I know that h and r are given, that's 10 over 4, I can solve for lowercase r, so lowercase r over h is 2/5 if you cancel the fraction, and then move h to the other side, lowercase r is 2/5 h. There it is. So now area of R was pi r squared, area, I don't know why I put h, I meant y, height, the lower one. I'm changing them all now. So a of y is going to be pi, and instead of r I get to write 2/5 y, everything squared, which is pi 4/25 y squared, which is 4 pi y squared over 25, to write it in one term. So now, to get the work, 0 to 7, because we are pumping all of the water out, or whatever it is. Rho g, right? Rho is 1,000 if it's a water, and then go up from there. G is 9.81, call it 10. Now we have our area equation, which is 4 pi y squared over 25, and then we have times 12 minus y for our nozzle height, which was at 12, and then dy. So to solve this, I mean, it's still basic integral, it just looks messy. You have your 4 pi over 25 rho g, that's all constants, kick them out, and all you need to do is to integrate y squared times 12 minus y, which you distribute, right?
What do you call that? Like, do you say it again?
Rho?
Row. Like row, R-O-W, row, or Joe?
R Joe.
R.
Computed from, come on, computed from 0 to 7, and that gives you a number eventually for work. So if you sit down systematically, look at this, right, you will eventually figure out what is there. They did the cylinder example, which is what I did. They did not do cone one. They did a scary example of sideways. So you can look at that one. Sideways cylinder. So you actually have 3 examples on this. There's one more type of problems here for pressure, right? Force and pressure, and they also have. This is you're designing a dam of some sort, or something that will be under pressure from water. Right, you're designing something that has to withhold a certain amount of pressure acting upon the area. I mean, I'm going to give you the formula, explain the formula. You can try an example. It's pretty much the same stuff like the previous one. You figure out the area, cross section, and that's the hard part. The rest you should just fly. So the force is the integral 0 to a rho g b minus y, same piece, and then w of y dy. This one is labeled as depth, and this one is labeled as width. Now, that's the formula for the force that will push. So force that will push against the dam or something. And then you would feed that into the integral if you need something else later that it's still evolving. So these problems are done again in terms of the y. They gave us the trapezoid looking dam that is 40 over here, 30 in height, and 20 on the bottom. So this is maybe in meters, whatever. It is meters. So this is considered the face of a dam. Yeah, ones the beavers make. And it should hold the lake, right? So the lake is pushing against it everywhere, right? There are water molecules adjacent to every point of this dam, face dam. So the pressure, right, is the force applied over the area. You ever wondered why those big military tanks have the wide, like those tracks? Couldn't they just put that thing on tires and, right? Or even make it a solid tire? Or how well would that thing work, right, on sand when it's that heavy? There's that pressure on the area, right? You can't take a small, tiny tire, even like 50,000 of them, and put the tank on it because it's going to sink, right? So wide, the wider the track, the more weight can it. And I think I like have like 300-gallon tanks for fuel on the thing. So it has to withstand the pressure of water pushing. You have the depth part and the width part, both calculated in terms of y, and then the regular, whether it's what's in a lake, right? The water or whatever else. And then you have gravity as well. So you can, they have over here on page 466, draw a y-axis on the face of the dam in the vertical direction and choose a convenient origin, also taken to be the base of the dam. So in our case, that first step is to draw a line like this, right? And draw and make sure that this point here on the bottom is the origin 0, 0. You do all of your measurements from there. And then it says find the width function w for each value of y on the face of the dam. So what do you have? If that's your new established x and y axis, you have the equation of this line. This point here is clearly 10, 0, and this point here is 20 and 30 up. You can find the equation of the line using your y equal mx plus b and slope and stuff. So you can find y. So equation here. Let me switch to blue because it's not that important. I solve it in terms of y, and just plug everything in. So try a few of these problems, and this is not a major point. So if I have to put anything on the test, it's going to be something with lifting, because springs are kind of dull, and this stuff is same as the previous one. So I'm mainly concerned with you actually designing the systems, like, you know, for gas stations, or pumping the water out of basement, or pumping the fuel out of the things like so you put the fuel into the burners, so all that kind of stuff. And this is So that will cover physics. We'll talk more about other stuff. Bye, stream.